So then this S1, this will create the carry out bit C2, whatever carry out comes out of it, of adding A1 B1 and S1. Sorry, A1 B1 and this C1. This C2 becomes the carry in from the for the A2 B2 bit, that gives me the sum bit as S2 and the carry out bit as C3, that comes as the carry in for the A3 B3 bit here, and eventually get S3. That is this S3, this one. And then the C out that is neglected from the result of the addition, that you have seen that whatever is the leftmost bit, whether it's 1 or 0, whatever it is. Obviously, if it is 0, then it does not have any meaning there. But if it is 1, it is also discarded. Now, though the fact is that in today's computer, this adder is called ripple carry adder. That means the addition from one bit, the carry from one bit ripples through the previous bits and so on. Whereas today's computer advanced, much more advanced adder, the disadvantage here, as you can see, that these bits cannot be added parallelly, right? For one bit to be added, it needs to wait for all the previous bits to be added, which obviously matches with our intuition of addition. But this slows down because addition is one of the most common operation that happens. In fact, arithmetic operations are one of the most common operations that happens in any calculations. So even even trying to minimize even by at the nanoseconds level is sufficient, because suppose if you can save some operation by an addition of 2 nanosecond, okay, and if that operation in a procedure say happens 10 to the power 6 number of times, right? So eventually, as you can see, that the amount, the overall slowness in the program, that becomes quite visible, right? Because if that operation happens 10 to the power 6 number of times, eventually the slowness will happen at least 2 into 10 to the power minus 3 second, which is high enough for in terms of a computer. And in fact, in a very large softwares, these operations happens, such common arithmetic operations can happen even at the levels of 10 to the power 9 or even higher. And as you can see that only these 2 nanosecond speed difference becomes visible in an algorithm when that operation is so much frequently used operation, and these arithmetic operations are one of them. So the researchers in the computer architecture always try to enhance it as further as possible, and today's technology use something called carry look ahead adder. Carry look ahead adder is a parallel adder that that can add the bits in parallel. And as I think you can understand from the name that carry look ahead means from the given bits already, it predetermines what is the possible carry that is going to come to this second one or to this third one or to this fourth one, right? It is determined already. And as you can think about, if you try out all the cases of A1, A0, B0, A1, B1, A2, B2, A3, B3, that will be an 8-bit input, and you can obviously determine specifically that what the carries are going to be, and from there you can create another circuit like this, but that circuit is extremely complex and highly advanced. So I'm not going to discuss here, but that allows you to calculate the carries in advanced. Doesn't matter whatever A1, A0, B0, that means whatever the 4-bit numbers you give, it will calculate the carries in advanced and then will produce the sum out of this. Okay, and these 4 adders will then work in parallel in such cases. But generally, such complex circuits are not designed for 8 bits or 16 bits because complexity of that circuit becomes unmanageable in that sense. So that are generally confined within 4 bits only. And then suppose you have 4 bits adder like this. I'll also show you one general convention. That means A and B are getting as input, each with 4-bit lines. 4 wires are going through this. This is a carry in. The carry out from here is passed through another 4-bit adder. So this 4-bit adder you can expand to 8-bit, 16-bit, and then you can add 4 16-bit adders to create a 64-bit adder, and so on. So you can expand it as you wish, as long as you have the corresponding cost limit in designing the circuit. And nowadays, these 4-bit adders are created using this carry look ahead adder. That's giving us enormous boost in computing. Well, so rather than diving into much more details, let me go into how the subtractor is designed. If you can remember that subtraction, if we do the subtraction, say A minus B, this is nothing but take 2's complement of B, which is, that means take the naught of B and add 1 to it, right? And then add it to A. This will give you A minus B. So you can simply use the normal adder, simple this full adder as it is to design the subtractor. Let me take this 4-bit adder. The design of this 4-bit adder is as it is, what you have seen in the internal design. The only thing is that Cin is now sent as 1. A goes as it is, whereas the naught of B is passed. Obviously, there are 4 NOT gates as well, right? 4 NOT gates sitting parallelly, which again I have drawn as shorthand. So the naught of B, A. So this addition becomes something like A plus naught of B plus 1, and this together is A plus minus B, giving you A minus B. So this is again that full adder. So simply set the naught of B and set the carry in as 1. This will give you the addition. This will give you the subtraction. So same circuit is used for addition and subtraction. And remember, control unit commands what operation to perform, if you can remember? If you can remember, control unit understands the instruction that is coming in. It decodes. In fact, by decoding, again, control unit is not some intelligent anything. Again, there is specific circuit, transistor circuit like this is there, right? Which simply this from the control unit if I consider the control unit something like this, though the circuit here is a special type of circuit that is called sequential circuit. That means it works on a time clock, but I'm not going into the details of this because that will be you'll understand about the sequential circuits when you study about the digital circuits. So maybe the instruction is coming over the lines, multiple lines, whereas is the instruction coming in. Whereas the circuit is set in between such that the commands are going to various locations. If the command needs to be sent to ALU, one bit will go towards the ALU. Okay, then maybe one bit is going towards the input output, the devices, the ports. Okay, maybe one bit is going towards the memory. I'm just showing three most common. In fact, there are hundreds of such wires are coming out of the control unit, each going to different parts of the your device, right? And all these wires coming out except the one going to the ALU, because the ALU is within the CPU itself. One part is maybe going to the registers. Okay, I'll tell you what registers are. Now this, so various signals are going to the various parts, and how these instructions are mapped to these signals, again truth table and design of the corresponding circuit. So maybe the instruction is something like, say, add, sub, multiply, or div, that means division. If the instructions are something like that, and also the 7 logic gates, the 7 logic operations, then the corresponding ALU, this bit is turned on. That means the command is going to ALU. In fact, it is not a single wire. Various signals going through this. As for example, let me know if it becomes difficult for you to digest. Say, suppose there is a full byte, there is a full adder. The Cin is coming in. This Cin is sent from the control unit. The A is there. There is a small circuit that is called multiplexers, that in fact decides which one to go. So eventually on this line B is going there, and on this line B bar, that means not a B is going, and one bit here determines which one of the two inputs will go. This such circuit can also be designed that determines if two inputs are there, A and B, there will be one output line. One input will tell you which of the two inputs will be shown on the output line. That means it will select one of the two based upon the input. If it is, say, if this line is 0, A will be here. If this line is 1, then B will be here, and so on. So it is a very good option to implement if else. Well, that's another part. So let me see if else at the circuit level. Now these marks, that means this input line, this signal, and this Cin line, they are both of them are coming from the control unit. So maybe if you say, if your command is add something, right, the control unit will understand that it is part of the ALU, remember, because this is the arithmetic logic part. Now if the control unit understands there is an add, say 10110 or something like that, whatever is the instruction for the add in this particular processor, it will send the 0 line here and maybe the corresponding line here to select the B line. So addition of A and B will occur if add. and 1 if sub. If the subtraction instruction is coming to the control unit, it will send a 1 on this line, and the corresponding signal maybe 0 or 1 that will select this this B naught line over this to send to the full adder. So it is subtraction. 1 is going here, A is here as it is, and B naught is going there. So it is subtracting A and B. And if it is addition, 0 is going here, B is going here, A and B plus 0. So addition is happening. So control unit is sending the corresponding signals to the after understanding the instruction. So that's how control unit in fact understands instruction. Okay. Any of you have any question? Any of you have any question or anything anything you want to ask?
Sir, I have a doubt in full adder, sir.
हाँ बोलो.
सर वो जो डायग्राम था ना सर, वो सर फिर से समझा देंगे?
This one?
नहीं सर, इसके जस्ट ऊपर वाला.
अच्छा अच्छा ये वाला ना. देख.
Yes.
Though I have drawn it, somehow it became a bit, that means rotated. Anyway, all my writings and someone don't know how it happened here. So suppose this is the sum bit. These two equations you can get via K-map or Queen-McCluskey method. I'm not going into the discussion of these algorithms now because that will drift our discussion into a complete different way. But somehow, suppose that these two algorithms exist, and if you employ any of these two algorithms, you'll get these two equations. Okay. Now, this A and this B, this is the B line, this is the A line. Now, what do you need to do here? A XOR B. So see, this is the XOR gate, right? So what you are getting out of here is A XOR B, right? And
ये जोर क्यों चूज किया सर ये?
हाँ?
जोर क्यों चूज किए हैं?
Because that is what has appeared as the equation. Okay, because that is what has appeared as the equation. That means this equation will solve this truth table. As for example, that means if you take any A, B, and C, say it is 0, 0, 0. If you perform this operation, you'll get 0. Okay, let me consider any one of them. Say 1, 0, 1. A XOR B is 1, and if you XOR that with 1 further, it will give you 0. So S is 0. Take anyone else. 1, 1, 1. 1 and 1 XOR gives you 0, and 0 and 1 XOR gives you 1. That's what you are seeing this. You can take any input here. If you perform the operation that has been demonstrated here, you will get the S. That means if you perform this equation for each input, you will get this S output. Is it clear?
Yes, sir.
And similarly, this C out here is similarly you can check it out. Let me take any one of them. Say 101 here. A B, and so 1 and 0 and becomes 0. So this is 0. B C in again 0 and 1 and so 0. Whereas C in A 1 and 1 1. So or these three 1 and 0 you'll get 1. That's what you're getting as C out. Right? Let me take any one of another one of them where you get 0. Say this one. Okay, say 1 0 0. So A B 1 0 you'll get 0. B C in you'll get 0. Where C in A 1 and 0, this time it is 0 now. So ORing 3 zeros will give you 0. So you'll see, you take all the inputs, you do this operation, you'll get C out always. Now if you ask how did I understood that this equation is satisfying this, for that you have to understand these two algorithms, right? But don't worry, here these full adder equation is already very well known to those who are for those who have studied digital. So this is already very well known. So I have written them directly. But if you go to if for any truth table, if you go by any of these two algorithm, you will get the minimal circuit. Okay. So these two equation will satisfy this truth table. This S for this S column and this C out for this C out column. And once you have this, then you'll get this circuit. This line is giving you A's or B. Then this C is here. This C is joining with the A's or B already. And what you are getting is A's or B's or C. The C. And that is what S is. Similarly, if you look into this, A and B, sorry, first A and C in. This A and C in, I have fan in the where. It is going via an AND, that is giving you C in A, this C in A part. Then this B, okay, I think I have minimized this equation a bit. Yes, if you look into this equation, AB plus BC in plus C in A, take the B common, A plus C in, and then take the B common, A plus C in plus C in A. So this is giving you the C in A part, right? This part. Then this C in and A, it is being passed by an OR gate. That is what you're getting here. This blue gate is giving you, this blue gate is giving you this one. Right now, after you get this B plus C in, sorry, you get this A plus C in. Sorry, in fact, I have just wait for a second. Wait for a second. I have garbled a bit while saying it so quickly. This A is coming here, and this C in is coming here, and they are going via the OR gate. This is OR gate. Okay, so A or C in, this is being given there. Along with this, you are multiplying this B line. You are multiplying, in fact, you are doing the AND with the B line. Not multiplying, you're doing the AND with the B line, and this is what you are getting. Whereas here you have that A and C in line, it is coming to an AND gate, and this is giving you this A and C in AND, and then you are going to OR with this green one and the red one. So that's what is happening here. The OR is happening between the green one and the red one, and this will give you the C out. Okay, is it clear?
So,
Bolo.
So is there a reason why you chose to do only like 4 operations? I mean, we could have even represented it using the 5 operations, right?
Generally, we always try to keep at the power of 2. If you can observe that all the operations happen in 8 bits or 16 bits or 64 bits because they are all power of 2. The reason to choose always power of 2 is that it gives you the full range. That means if you do the operation in 8 bit, as you can say, if you do the operation in 4 bits, you can easily represent that using hexadecimal, right? Because hexadecimal covers the complete 4 bits that you can use. In other way, In fact, it is always the power of 2 that is always chosen for any operations or in terms of computers and any digital circuits. Okay, it's always power of 2 that is chosen. Does it answer your question?
Yes, sir. Okay.
So, any other query? Okay, so now let me discuss the next part, that is a bit still inside the computer. Now you have seen the here. Let me discuss about registers at first. The circuits that you have seen till now, they simply take the bit and release it. Okay, they simply take the bit and release it. Whereas if you consider the memory, it keeps your information. The ALU or control unit that you've seen, it takes only the input, performs the operation, and done. It does not remember what was there. But whereas if you consider about the memory or these registers, right, you'll see that they can hold the bit. They can hold the bit. So how such designs are made? How in fact they hold the bit? As an example, let me draw a small circuit. Two NAND gates have been placed here. This is one of the most common basic register. In fact, if you see, this is called SR flip-flop. If you see that, suppose you are passing S as 0 and R as 0. S0, R0. That means both of them are at low voltage. When S is 0, check out. If Q naught is 0, what will happen? 0 and 0, 1 will go out of the Q. Okay. Whereas if it is 1 here, 1 will come here, right? And this is also at 0, so 1 will be here as well. Rather than putting the NAND gate, let's elaborate it first using NOR gate. That will be easier to consider. Because anyway, I'm not going to discuss it at the advanced level. Just the essence that circuits designed in such manner can hold information. Let me replace it into the NOR gate. Yes, NOR SR flip-flop can be designed using either NOR gate or NAND gate. So if S is 0, now suppose Q is 1 here. Okay, Q suppose it is 1 here. S is 0, R is 0. 1 and 0, 1, and you'll get a 0 here. Whereas as it is 0, 0 and 0 NOR gate, it will keep 1 here. So observe that it is somehow in a deadlock. It is not getting out of the state. The Q, it is if S and R are forever in the state 0, Q will forever will be in the state 1, and Q bar will be forever in state 0. Check it out. if S and R both are always kept at state 0, does not matter what happened, Q will always be forever will be in state 1 and Q bar will always be in forever state 0. Right. So it is somehow has held the state Q. Obviously, this is one of the most basic flip-flop. There are much more advanced flip-flop, T flip-flop, D flip-flop, D flip-flop that holds the data within itself. It can be designed in such a manner that it will hold the data within itself. Whatever there is in the case of D flip-flop, all flip-flops always has two lines, Q and Q bar, and Q and Q bar they will always be in reverse states. That means if it is 1, it will be 0. If it will be 0, it will be 1. Now in D flip-flop, Q will there you can keep in fact another input here that we generally in fact the clock signal, but I'm not going to the details. Q will take D. Now varying the depending upon how you are going to design the clock signal, you can vary it. Maybe when clock will be high, Q will take the value of D. Right? It can be designed in such a way. I'm just saying an example because there can be various types of design that can even be done within D flip-flop. Just like in the SR flip-flop, you can do with a NOR gate, any AND gate. Each design will give you different functionalities. Similarly, each flip-flop, there are multiple ways to design each flip-flop. One possibility is that if clock is high, that means it is 1, Q will take D. That means whatever is coming to the input will go to the output. Else, Q will be in its own state. That means suppose somehow at some moment you suppose you want to store some data. You make the clock high, send the data through D. Q will hold that, make the clock down. That data will stay in this flip-flop as long as you do not make the clock high again. Okay, so that's why again this is the example where clock becomes high. There are examples when the data will be stored when clock will be low. These D flip-flops can also be designed in such a way that the data will be stored here when clock goes from low to high rather than staying high, or well they are in fact going to the bit depth of complexities for you now. So just in an essence, what I want to convey is that flip-flops can store bits within itself. Okay. And just what I was saying here, if it is 0 1, as you can see, it is 1, so Q bar will be 0. And if Q bar will be 0, you can be rest assured Q will be 1. Because 0 will go here, 0 and 0, and eventually 1, sorry, 1 0. If it is 1 0, you can check it out, this will be 0 1. Whereas if both S and R becomes 1, this is invalid state. But I'm not going into the details. But main interesting state is this one. Q stays in state Q, Q bar stays in state Q bar. So this in fact holds the information. This is just the most basic flip-flop, Then comes the JK flip-flop, then comes the T, D. The D flip-flop is used to hold the data. So flip-flops can store bits within itself. Okay. Now, just like you have seen, we can put one adder to create 4-bit adders and so on. Set multiple flip-flops to store, say, byte, say 8 bits, 16 bits, whatever, even 64 bits. It depends on how many flip-flop you are going to put, right? So maybe you put a D flip-flop here. This is, suppose you are going to store the bit, say this is the say this is the B1, this is the B0 that you want to store. It will be stored as the B0. There is another flip-flop, D flip-flop, and if you want to store B1 and so on. Let me create a 4-bit register. Again, there are multitudes of various registers possible. I am drawing the most common one. And put a common signal to this. So what happens here is that suppose we want to store this 4-bit B0, B1, B2, B3. Though generally it is kept from the left to right, but somehow I drew it. Maybe you can make it B0, B1, B2, B3, and so on. Similarly, Q0, Q1, Q2, Q3, but that's obvious. Anyway, so suppose you want to store this 4-bit data into the register. Whenever the clock will become 1, you have already fed the data into this B0, B1, B2, B3. They are already on the line. Whenever the clock will become 1, this register will store your data. Right? There are Q0 lines via this, but we always ignore this. These output lines lead to nowhere. These output lines are generally grounded, and we are not. They are simply the byproduct of the circuit, nothing more than that. We ignore these lines. These Q0, Q1, Q2, Q3, they keep this data held within the registers. Okay, and today's processors keep 64-bit registers. And these registers, they stay, they are, in fact, it is called, on the VLSI, transistors are etched, so it is a very common term. They are etched, that means they are placed. They are etched on the processor chip itself. That means so now, in the simplest term, we can divide the processor into these 3 regions. One is your ALU, this is your control unit, and there are various registers sitting here, 64-bit registers. Okay, so this overall is just a schematic of a processor, today's processors. Any of you have any question till now? If you found it difficult to understand, don't worry. Rather, focus on the core part, that these registers can hold data. Okay, I just discussed this for the sake of completion, that it is possible in digital circuits, nothing more than that. But digital circuits can hold data within itself as well by putting it into a loop, like as you can see here. It has been put into a loop continuously. The signal is going on these lines continuously, and it will be stuck within that particular flip-flop. And so, okay, so these registers can hold data. Now, let me keep the memory here as well. Suppose this is the RAM. If you can remember that RAM has multiple rows in it. On a 64-bit machine, in fact on a 64-bit processor, the registers are 64 bits. Okay. Now, the address, in fact, each row, this is important, each row in RAM has its own address. So generally we start the address from the lowest most byte, and we increase on this direction. So maybe this address is 0, then it's 1, 2, and so on. Maybe this is the row with the highest address in the RAM. Okay, each row in RAM has its own address. Now, generally on a 64-bit machine, from now on, whatever you're going to consider will be about 64-bit machine, because that is the today's machines. Addresses are also of 64 bits. So addresses are also of 64 bits. Now, how will you write the address? Say maybe the address of say certain row is 0, 0, 0, 1, 1, and so on. There are 64 bits. Suppose this is an address. Let this be an address. Every time, will you represent this address by writing these 64 bits? That will be too cumbersome, right? So there is a shorthand. Can you tell me, if you represent this using hexadecimal, how many digits you will have to write? Anyone?
Sir, 16.
Yes, only 16. So maybe is 0001. So 1, B, A, 2, 1, 0, 5, 6, 2, 1, 9, 8, C, 0, E, F. It can be a valid address. Okay, and obviously you do not need to write these 16 bits, because each 4-bit directly gets converted to one hexadecimal digit. So maybe if it is B, maybe it is here, it is 1011, right? So that will give you the B. A is 10, B is 11. So on the next one will be 1010. So this 64-bit address, maybe it is representing some row here, some hypothetical row here. It can be written smoothly using these 16 hexadecimal digits. So that's what hexadecimal is so much important. When you have to represent some large number of bits, write that in hexadecimal, because that is a 1-to-1 correspondence between these two representations. without any need of any addition, without any need of any division or multiplication. Well, now let's take it. Let's take a bird's eye view about what is then happening when an application executes. Suppose this is the hard disk here again, and the application is sitting here. Okay, and in the RAM, maybe I'll tell you later who takes the decision. It is operating system that takes the decision where to load. Maybe suppose this is the part of RAM where operating system has decided to load this application. So this application comes here that you have seen previously as well. Each 8-bit, say this 8-bit is, say I'm writing in hexadecimal now, so 05. So the 05 will come here, right? This byte. Then maybe the next byte is A1. So A1 byte will come here, and so on. Okay, and it will go in the same way. Now, after it is loaded, so application is loaded into RAM from lower address towards higher. Okay. Then CPU is informed where the application has been loaded. That means suppose this is the processor here, and how the CPU is informed? There is a special register in the CPU that is called instruction pointer, IP. There is a separate point, IP instruction pointer holds the address of next instruction to execute. So maybe suppose this application has been loaded here. Okay. After loading this, operating system will do this job. Okay. Operating system will, in fact, it does much more than this, but let me keep this simple for now. Operating system will load this instruction pointer register with the starting address, with the address of the starting instruction of your application. So maybe that suppose Firefox has been opened here. The browser Firefox has been opened here. The Firefox is residing in this region of the memory. Now, after opening Firefox, the OS will tell the CPU that this is the starting address of the application that I have loaded. Put it in your instruction pointer, and CPU does that. And once CPU has received the address in the instruction pointer, obviously the next instruction the CPU will execute is this 05 then. That means this instruction will then come to the control unit part. Okay. Now, several things are here. First of all, let me go into a bit more deeper. There are three types of buses. In fact, bus means a bunch of wires in simplest terms. Three types of buses. One is address bus. Address goes from CPU to RAM. For now, I'm considering RAM. Later on, you'll see that multiple devices have addresses. As for example, if some of you have some dedicated graphics card like NVIDIA or AMD, it also has its own video RAM. That means it also has address. Well, but all these addresses are generated from the CPU, and these address bus goes from CPU towards the RAM, but it does not immediately reach the RAM. I'll tell you why. Data bus. Data passes through this bus. And it is bidirectional. That means the data can come from RAM to CPU or CPU to RAM. Whatever. It can go in both directions. Whereas control bus, it generates from the control unit. It generates from the control unit and goes to all directions within a machine. That means, and it carries, in fact, there are a bunch of words, it carry the control signals. Remember the control signals I discussed here? That ALU, where did it go? The previous slide, I think. That ALU, after getting the instruction, it decodes, then it sends the various signals. If you have to do the addition, it sends the ALU. If you have attached a USB on some port, the control unit sends the signal to that corresponding port. Right. So the signals starting from the control unit, it goes through all the directions over your motherboard. If you open up your machine and if you see the motherboard, you'll see that all the ports are in fact on your motherboard. Okay. So, and control unit, motherboard is nothing but in simplest term, it can be said as the playing ground of the computer. Okay, it's already 3 p.m. Okay, so I'll discuss the rest of the part in the 5 to 6 class. Okay, how these buses communicate together. And I'll also take the questions then as well.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Welcome. Because it is already 3 p.m. I forgot that it's so much time has passed.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.